Hello. Let us see the part B solution now of internal exam that we had. Continuing on the earlier recording, now let us look at the question 11. Convert the following binary number to octal format. So let us use the simpler method of finding out 1011 00 111 00 in binary form. So as I mentioned, we can divide that into 3-bit patterns because we need octal numbers which vary from three zeros to 111. Zero value is 0 and 7. Now hexadecimal is a continuation of this into 4-digit numbers up to this, which is 8 to 16. So since there are no numbers left out in between in the octal system as well as in hexadecimal system, none of the bit patterns are left out compared to the binary number. So it's okay when you have a binary representation to find out its equivalent octal form or a hexadecimal form. It is easier for us to just divide the patterns into either 3-bit or 4-bit patterns and then write down the equivalent values of those numbers in the system. Now this, if you want, you can add a 0 here because it is not going to change the value. Now you can write down what are the values that individually these bit patterns represent. This is 4 and this is 3 and this is 4 plus 2 6 and this is 2. And now it might look like a normal decimal number, but you should remember to put octal number because we are looking at an octal representation here. Okay, it's not a decimal representation, so this is the right answer. Okay, and if you miss out this 8, maybe we should reduce the mark, but since we had asked for a octal format, we could give the full marks, but it is very important that you represent this and mention whether what system it is. Otherwise it can be misinterpreted as a decimal number, which is not correct. Okay, I hope this is easier. Now let us look at the question number 12. Construct 5-bit even parity generator. Now I have already explained as a part of part A explanation what is a parity, odd or even parity. Now we are looking at the even parity generator. That means we are going to feed the data, whatever data we have. Okay, let me call it as D0 to some D7. This data is going to be fed to a parity generator. This, I'm not saying that everything is 1, but some bit pattern. The parity generator is supposed to generate the parity bit. Now, what is asked in the question is an even parity generator circuit. That means it should count the number of ones and then generate a parity. Now, which one will you be using it? Okay. Of course, it is mentioned that XOR gate needs to be used. So that's what is normally used for generating the parity, which I have already covered in the session here. Okay, which is already given. Let me explain something about the parity generator here. Now, what is an XOR gate? Why are we using XOR gate? That you must be knowing it from the explanation in the class, but let me recall what was discussed there. Now, let's suppose we are giving two inputs to A and B to an XOR gate. Now, let me call this as A and B, and then this is the output O. Let us write it like this. Now, 0 0 0 1 1 0 1 1. So we know XOR gate gives output 1 when the input patterns are not same. 0 and 1, it is 1 1 0 1, and other two things are 0. Now, what exactly is it doing? The XOR gate is doing what? Now, whenever input is having odd number of ones, it is giving a 1. Otherwise, when it is even number, it gives a 0. Even not having any 1 is also equivalent to even number, so it gives a 0. Now, in another form, we can even consider the XOR gate as counting number of ones and generating a output 1 if there are odd number of ones. Okay, odd number of ones are there in the input, it is going to generate a output 1. So if I am using the XOR gate and then I want to generate parity, what will happen? Suppose if I have an input, so we understood that XOR gate generates 1 if there are odd number of inputs. So it finds if there are odd number of ones in the input as far as a single XOR is concerned. Now what if I add one more XOR? Will that also do the same? Yes, you can check it up. Now suppose if I give 0, 0 and 1, now odd number of ones are there. This 2 XOR gates should give me a 1 if I have to say that any number of XOR gates will give me a 1 if there are odd number of inputs. So let us check that now. 0, 0 will result in a 0 here, and then we are giving a 0 and 1 here, so it will get the output 1. That means if I keep adding an XOR gate, it's going to count the number of inputs whether they are having odd number of ones. So that is very clear. Now, how do we use it for a parity generator? Now, what is happening is, now we have some pattern and we are going to use the XOR gate. If we just use the XOR gate, it is going to generate a 1 if there are odd number of input. Now, what we do in a communication channel, we give the data and then along with the parity, we send the data. All right. Now, parity is also sent. Now, if I had fed an odd number of ones in the data, if there are odd number of ones in the data, this XOR gate, just a set of XOR gates, would have generated a 1 to me, and I would have put that 1 also as a parity here. That means what? It is going to be used for an even parity, because along with this 1, I am making it even. So whatever may be the data, if there are odd number of ones in the data, I am going to make parity bit as 1. That means I am generating a even parity here. So if I use only the XOR gates and the inputs are given, then we are generating even parity. Now, what do I do for odd parity? Just complement it. So that means if I, instead of XOR, if I use a XNOR, the output will be complement of this. So it will be 1, this is 0, then 0, this is 1. So if I put a NOT at the end, then it's going to give me a 0. So I'm going to put a parity as a 0. That means odd number of ones are there. My parity is going to be 0. So the overall number of bits in the data along with the parity is going to be odd. That means if I put a NOT gate in front of it, that which is nothing but XNOR, I am going to generate an odd parity. So this, even if you don't remember the circuit, it is easier to draw it. So if you remember the 4 input data, which is odd parity circuit here, what is asked is 5-bit data bit. Now, what you need to do is add one more input to the existing odd parity generator, and then this NOT should be removed. It should be moved to the end, and then we should show this circuit. Now let me show you what I mean by what is the solution for this. So this is the solution. Now we wanted even parity, right? The question said 5-bit even parity generator, and we just now saw in the slides even parity does not have a NOT gate in front of it. So you have this circuit, then add one more input and put a XOR. That's all. So this is the solution for question number 12. I hope this is clear. Now what is question number 13? 4-bit XNOR gate. We are giving a XNOR gate here and then a 4-bit input. Draw the truth table for it. Now you know that truth table means it has to have all the combinations of 4 input, which are 16 numbers. Now what is the output? Now just now I told you XOR gate counts odd number of ones. It is 1 when odd number of ones are there in the input. Now XNOR will count even number of ones. It will be 1 when there are even number of ones. So it is easy to find out what the value should be. Wherever even number of ones are there, we should generate a 1. Okay, that means 1 0. So 1 0 has an odd number of 1. Now XNOR is going to give you even number of, it is going to set even number of ones as set to 1. So it will be 0 because this is odd number of 1. This is also going to be 0. This is either even number of ones or no ones are there, then it will be 1. Now what about this? This is 1. Here odd number of 1 is there, so it's 0. This is also 0. This will be 1. This is 0. This is 0. This is 1. Even number of ones are there, so this is 1. This is 0, 1 and 0. So this is the output that you will get. Okay. Now one number is missing out. 1 second. Okay. So let me show all the numbers. So 1110 is odd number of ones are there, and this is even number of ones. This is 1. So this should be the output truth table, and you don't need to remember or memorize this. It's based on basically counting number of ones in the input and then generating a 1 for it. Okay, I hope this is clear. Now let us solve question 14. So let us start from this point, the just below the 5 volt, and then since I is shown to be flowing in this direction, we have to traverse through this circuit till we come back. It's applying a KVL here. Now one more thing what you should remember, whatever terminal that you come across, that voltage should be written, and then since current is assumed to be flowing in the right direction, in the clockwise direction, it is entering the resistor. So as per the passive sign convention, a current entering the passive component will be having a positive voltage. So we have to write plus 2I. So if I is shown inside the loop, that means that is the current which is flowing through this wire also. There is no difference between the current which is flowing through the wire as well as what is shown here. They are same. So now let us start from the 5 volt supply that we have. Let us put a 5 here, plus 5, because we are encountering a plus terminal of the voltage source, and then current is entering the 2 ohms resistor, so it has to be plus as per the passive sign convention, IR. So let me write 2I. Okay, I is the current which is flowing. Now minus 1.5, then another minus 1.5, then plus 2I, and then plus 2I, then plus 10 volt, and minus 1 and plus 2I equal to 0. So how many are there? Resistors, 2I, this many are there. So this will be 8I, correct? Now the rest of the things, we can say minus 3 and then 15. This is minus 4. So 15 minus 4 is 11. So we have 11 here plus 8, because 8I is all positive values, and that is equal to 0. Now we need to find out I value. So do not forget the minus sign. So minus 11 by 8. So remember to put ampere, and since you are not using the calculator, we don't expect you to write the expanded value, but the calculated value, this is the one. So we will be giving marks, complete mark, a full mark, if you have this answer. But if you have missed out minus, we have decided not to give any marks because that is completely wrong. Okay, I hope this is clear to you. Now let us look at question 15. Okay, this is similar to what we solved it using the model paper. So let me explain again. I gave you the solution for the model paper also. Now look at this circuit. Maybe I'll draw this for a clarity purpose here. 5 volt, then resistor is there, R1, then another one. Now this is 2 ampere, what is flowing here. So if this is a current source, please remember I have already told that it's an independent current source. So it is going to drive 2 ampere of current going through this. Now what is shown here is a 1 ampere current here. Well, again this shows that this much is flowing here. So this is 1 ampere. As I told you, the current what is shown is same as what is flowing into the resistor. So this is some R3 resistance, doesn't matter what value of that resistor is. This is some resistor R1, R2 and R1. Now this is the point is shown as A, and the question says that in the circuit below, assume that the potential at the point A, which is named as VA, is 3 volt. That means this voltage at point A is VA, which is nothing but 3 volts. So what is the voltage at this point? Because there is no component in between. So voltage here also will be 3 volt, correct? Now, what is the voltage at this point? This is 5 volt from the ground. So this is 5. Now, there is a current shown here, which is 4 ampere. Okay, I am drawing it here. It doesn't matter. So what is happening is 4 ampere is flowing through the resistor, which is shown to be here, and it will come here. So 4 ampere is flowing through the resistor R1, and the voltage difference between the R1 is here 5 and this is 3. So VR1, if I have to call this voltage across R1 as VR1, which is nothing but 5 minus 3. Okay, 5 minus 3. So which is nothing but a 2 volt. Now 2 volt is the voltage across R1 and 4 ampere is flowing through that. So V is equal to IR. We know that. Now we know the value of I and we know the value of V. V is 2 volt and current flowing through this 4 ampere. Now what is R? V by I. Voltage is 2 divided by I is 4 ampere. So this is 0.5 ohms. Okay, this is the value that you need to write. In engineering notation, you can write it, or even if you write by 0.5 volts, 0.5 ohms is fine. Now, R1 value is found out. Okay, that is 0.5 ohms. Now, what is the value of I2? That you need to use KCL. Now, what is I2? I2 is the current flowing through this resistor, which is I2, is nothing but the current here. Now, since 2 ampere is coming into A and 1 ampere is going into R3, the rest of the current will be flowing here, which is nothing but 1 ampere. Now, this 4 ampere coming in will also be here, so which is 4. Now, at this point, if you see, 4 is coming in and 1 ampere is coming in and I2 is going out. So, I2 can be written as 4 coming in and 1 coming in, and that will be the I2. So it is 5 ampere. That's all. So this is a simple, and you don't need a calculator for it, and I'm sure you might have done this correctly. Now let us go to question 16. Now this resistance are shown as a components, some component, but I am mentioning that they are all resistor. Now how are they connected to each other? Okay, see, though it is shown as something like inverted V, they're all in parallel. Okay, so this can be written in a usual way, whatever you have been familiar with is this. So what are the values? This is 1 ohm. I'm not writing the ohms here for simplicity here. 2 and 3. Now how do you find the equivalent resistance across this? You need to find out the parallel resistance of this and then the equivalent value. So I will find the parallel resistance of 1 and 2, which is these two resistors, which is 1 into 2 by 1 plus 2. So 2 by 3. So this will be 2 by 3, and then another 3 ohms is here. So what is the equivalent resistance of this? Again R1 into R2. So just to recall the parallel resistance equation, R1 R2 parallel resistance equivalent is R1 R2 divided by R1 plus R2. So that equation if you have to apply here, now 2 by 3 into 3 divided by 2 by 3 plus 3. So we can cancel this out. 2 divided by 2 plus common denominator 9. Then that 3 will go here. So this 3 into 2, 6 by 11. So it's enough if you write the answer as 6 by 11 ohms, or the actual value is 545 ohms. So ohm is important. Okay, this is the answer. Question 16. Now show the directions of the three currents in the transistor. This is already, we have the thing which is already explained in the section 1.8. This slide is taken from. So just to recap on what has been covered in the transistor circuit, this is the flow of current which is shown. This is NPN transistor. What is given in the question paper is a NPN transistor, and power, the bias is also shown. So based on the power supply, you can easily find out that IB will be here, the direction of IB, and this is the IC, and this is IE. This is what you are supposed to mention as current flowing through them. Either you can show it along the wire, or you can even show it like the outside arrow. It's both are same. Now another thing what has been covered in the class is emitter current is equal to base plus collector current. So this equation is a must. You should write it. Then only you will have this directions would have given you would have given it correctly, because we can assume this transistor as a point because it is not storing anything, and whatever current coming in has to go out. So IB is coming here and IC is coming, then IE will be the output. So IE, if you apply KCL here, IE is equal to IB plus IC. Now the explanation what is required is, you can talk about how the transistor construction is, or even you can explain about the power supply, and whatever explanation you give, if it is meaningful, we have decided to give marks for that. Okay, so but what we expect it, at least the directions of the current should be correct, and the relationship between the current should also be correct. So that's about question 17. Now question 18, which is a continuation of what I have explained about signed and unsigned representation. And if you have not seen the part A solution video, please go through that first and then come here, so that I assume that you have seen that, and then I'm not going to repeat the same thing what I have explained there in the solution for part A part of this exam. Now the numbers or patterns are this. So 4-bit numbers are given. Okay, both are binary numbers. Now as I mentioned, you need to treat it as unsigned number and understand the result, and treat them as a signed numbers and understand the result. Now addition what is going to be performed is going to be the same. It is not going to be different, but how you are going to look at the answer is going to be the difference here. Now what is this value? This value is 6, and in unsigned case we are not going to treat this as a signed number, so the MSB is not going to be considered as a negative value, because it is set, then we will assume that it's a 2's complement form, but we are not going to see this number as a 2's complement form. It is as an unsigned number. As I told you, unsigned numbers vary from 0 to 15. So now what is the equivalent value of this? It is 13. Now this we know based on the number pattern, and then we know that it's going to be treated as an unsigned number, so we are writing this as 13. But what is the result going to be? It's like a simple addition. It is going to do the same full adder addition. So let us do the addition here. Now 1, it is going to have a 0 carry here, 1, and then it's going to have a 0 carry. Now this is going to be 0, and it is going to give us a carry as 1, which is again going to be a 0. Then there is going to be a carry here coming out, and this will be a carry. Now, as I have explained in the class, in unsigned case, carry indicates that the carry which is coming out of this addition indicates that this has overflown. Now, one more thing we should remember, as I mentioned in the class, that 4-bit addition, when we are performing, the result what we see is also considered to be 4-bit. Okay, so we will interpret this only, and because this is unsigned value, this is just a 3. But will you get 6 plus 13 3? No. So this is wrong. Okay, what you need to write is, in unsigned it is wrong. It's enough even if you don't mention about the carry flag, okay, which is set, but the actual result what you got itself very clearly says, we know that 6 plus 13 is not 3, and we got it 3, so it should be 19, but we got it 3, so it is wrong. Now let us look at the signed value. Okay, now the same addition is performed in signed also. Maybe I will repeat the same thing here just for the clarity purpose, but it's not anything different. The addition is same, the result is also going to be the same value, and there is going to be a carry flag here. Now let us follow the carries which are coming, okay, which I'll be using the hardware circuit and then show you shortly. So this is 0 0 1 and 1. That one is here. Now one thing we need to remember, in the signed addition we are not going to look at the carry flag, which I explained you, which is not going to be considered for the signed flag. The results are same, both the flags, you have a carry flag set, but if the software knows that it is going to be a signed addition and the numbers given are signed numbers, then we are not going to look at the carry flag. Now what are the representations of these numbers first? Let us first look at that. Addition has been performed by the circuit, and we are also done it with our knowledge of binary addition. This is again a plus 3, whereas 1101 is going to be considered as a negative number because we are doing a signed arithmetic. So when we are interpreting it, we are going to interpret it as a signed number. Now what is the equivalent value of this 1101? What is the signed representation of this number? So let us look at that first. Now 1101 is a signed number because it is 1, MSB is 1, so we are going to make it complement of this and then add a 1. So 0 0 1 1. So it is minus 3. So this is minus 3. Now what is that? What did I write here? So I have written plus 3, which is 110, which is not plus 3. So sorry about it. It is plus 6, right? It's not 0011. It's 0110. So this is plus 6 and minus 3. And the result what we got is MSB is not set. So it is plus 3. Now 6 minus 3 is 3. Now this result looks correct because we know as a human being, we know that this addition is subtraction is correct because it's treated as a signed number and then this addition is performed. One more thing you remember, though we are treating it as a negative number, the same addition is performed here. Okay. Now, how does the computer know whether this addition is supposed to be correct or wrong? So this I have explained in the class. Even if you are not written this detail, it's okay, but at least for the completeness sake, I'm going to explain it here again. So we have to look at the these two carries. Okay, when we are performing a 4-bit addition, here we are assuming that the ALU is 4 bit. If you need to find out whether the given answer is correct or not as far as the signed numbers are concerned, which is nothing but plus 6 minus 3, this carry, there are two carries are there. This is the one carry which is coming out. In our unsigned case, we only bothered about this carry, which is the outermost carry which is coming out. Whereas for signed arithmetic, the hardware is designed that we take this carry as well as this carry output. So both happen to be 1, which is fed to an XOR gate. In the hardware, there will be an XOR gate and it will set one flag, which is a output of an XOR taking two inputs, which are two carries coming out. Okay, if it is a 4-bit ALU, this will take these two carry. If it is 8-bit, it will take the last two carries coming out. So here in this case, it's going to be 0. So this indicates a overflow in the case of signed arithmetic. If this flag, which I call it as a flag, if it is set to 0, it means that this arithmetic, if it is considered to be a signed arithmetic, then there is no overflow. So what happens in the real hardware is we will look at either this flag or this carry flag, which I told you in earlier case. Any one of these two flags will be looked at to find out whether the result that we have computed is correct or wrong. The hardware does not know whether it is performing a unsigned arithmetic or signed arithmetic, because you know that it is performing the same results in both the cases. Only thing is, in the unsigned case, only this flag was looked at, whereas this value, these two flags, whatever I showed you, which is resulting into the overflow flag, is not looked at. In signed case, this flag is going to be looked at. So there are some instructions in the processor which will be used to verify one of these flags when the addition is performed. Now, who will take the decision of using this one of these flags? It is a compiler, because when you declare in your C program an integer, you will call it as unsigned int ui equal to some value 10. Now I may get signed int also. I may declare si, suppose I am calling it as minus 5. Now whatever is going into this variable will be a 2's complement of 5. That is, who will do? The compiler will make sure that a 2's complement is found, this value, and then put into the variable. So then when I am performing addition or si plus plus, when I do, it will be considering as a minus 5 is getting added to 1. So it will perform the same addition and it will interpret the result as minus 4. When whatever result it gets, it will be considered as a minus 4. So this checking whether this resulted in a overflow or not, we have to check the flag inside. There are some instructions that we will be doing it, and you will understand it when microprocessor course is conducted. And now right now what you need to understand is, if you are given the answers as wrong answer for unsigned arithmetic and correct answer for signed, it should be fine. You don't need to explain overflow flag or carry flag, but you will be welcome if you have explained it, because at least as a teacher I would know that you have understood this concept very well. Okay, this is a very important thing which you should all know. Okay, I hope this question 8 is done now. Now let us look at the question 9. Maybe this is also similar to what I have explained. Now we are going to look at the actual circuit to see the actual whatever I explained you working in a hardware. Now, just for a completeness sake, let me explain you. The full adder is nothing but the circuit which is shown here, constructed using half adder, and the half adder circuit is given here. Now, what is really asked in the question? Let me just look at the question now. The question says, draw a full adder circuit and give a sample input and write the intermediate as well as the final output values. Now, what you might have thought that I am expecting only this, because this is the question from the lab which you constructed it. So it is enough if you draw this, and then inside of it you can mention what are the gates which you have used in the lab, and then sample input. Suppose I say 0, 1, 1. Now when I am adding 0, 1, 1, what will happen? The sum will be 0, supposed to be, because if you are adding a 1 and 1 plus, sum will be 0 and then there will be a carry coming out as 1. Now carry should be 1 and sum should be 0 for this input. Now let us backtrack and see whether it is really happening. Now inside of this half adder is there, so you can assume that this 2 or XOR is there. What will happen? Because 1 1 if you give, XOR will be 0. Now let us fall through this. Okay, this is going to be XOR again. Now this is again 0 0, so output will be 0. XOR output will be 0 for same input. So sum is correct. Now what about the carry? Now you are going to have the same input is given to a AND gate. So let me say this is AND gate. Now both input are 1, so AND will be 1 here. Now what about this? Here both are 0, so this AND gate will give you 0. Now you get a 1 here and 0 here, so 1 has come. So this is the what I expect you to do, and we will give you marks if this is explained and you have drawn this circuit also correctly. Now what if some of you have written this picture? Okay, then it is going to be a little complex for you to explain the whole thing, but let me, for a completeness sake, I don't expect you to do the complete thing, but if somebody has done it, it's okay. Some sample number you have taken and then added it. Now I'm going to take the same number which we added it in the previous question example. So it is plus 6 and minus 3, which we know from the signed arithmetic. And if you are performing a signed arithmetic, then result will be 1 1 and carry will be 1, right? Carry is here 1. This is the carry 1 and this is another carry. This we remember it to be 0. Now how do we do this in the circuit? Now what happens is, when we are trying to do the minus 3, it is not going to be fed as minus 3, because this circuit is saying that this is equal to 0 if it is performing addition operation, and if it is equal to 1, it is going to perform a negative operation, minus operation. So we need to give, okay, the same number. If you give, it is going to find the 2's complement of this and going to add. So actually speaking, we are adding, instead of this number, it is minus 3, will be just, we will make it as 0 0 1 1. Okay, this is the input we consider as a B, and this as an A. And then if we need to do a perform a minus operation, we will say that S is equal to 1. Okay, if we are doing a signed operation, we will make it S is equal to 1, which is signed operation, and unsigned operation, it will be S is equal to 0. Okay, now let us fall through. These are the numbers. Okay, A and B are going to be these numbers, and let us give S equal to 0 and then perform addition. Now if we are adding a 6 and plus 3 is going to be 9. Okay, so this circuit is not full-fledged arithmetic what we have performed, and I am explaining it because some of you might have taken this circuit and then try to explain it. So let us say A is this, and 0 1 1 0, and then B is, I have to maybe use a different color, 0 0 1 1. So this is 1 0 0 1 1. So B is 0 0 1 1 and A is 0 1 1 0. So 6 plus 3. If it is a, I am assuming it to be feeding a positive number here. I am just trying to show you this result, how it will be shown in this circuit. Okay. So now what will happen? Now S will be 0 for our case. If we are considering it to be a unsigned number, S is equal to 0. Now later on we will do the same thing with S is equal to 1. Now S is equal to 0. This will be 0. This will also be 0. This is 0 because S is connected here. Now whatever input is coming, okay, it will be 0 and 1 is 1, and 0 and 1 1. This is 0 and this is 1. That means okay, sorry, it should be 0 here. B3 is 0 because B3 here is 0. So let me draw it as a 0 here. Now what will happen? We are getting the same number, and then this is 0 1, and I think I should put it in red so that consistency is there. This is 0 A is 0 here, this is 1, and this is 1, and this is 0. Now what is S? S is equal to 0 here, so it is coming as 0. Now these three input 0 and 1 is given, added, so it will result in 1, carry will be 0. Then this 3 input 1 1 0 is added. In that case sum will be 0, carry will be 1. I hope you remember. And then this is again 1 1 0, so sum will be 0 and carry will be 1. Okay, this 3 input, and here 1 0 0 input, so this will be 1 and carry is 0. Now if you perform a simple plus arithmetic, because we are adding a 6 and 3 now, so this will be 1 and this is 0. This is what is shown here, this carry and this is carry, and this is 0 and 1. So the result is 9 and the carry is 0 here. What has come out of this addition is 0 here. So this is ignored and 9 is the correct value, because 0 value is means that the unsigned value arithmetic is correct. So we not ignoring it, but this shows that the unsigned arithmetic is correct. So plus 9 is the answer. Now what if I am doing a signed arithmetic? So let me erase this. Now I am performing a signed arithmetic. Okay, in this circuit I am using it as a this circuit and then performing it. So let us do it now. A is plus 6, okay, which is given as 0 1 1 0, and this we are feeding. Actually we'll find the actual what we are doing is plus 3, okay, and when we are feeding the same numbers we are feeding, okay, plus 3, but we are going to be doing a minus arithmetic, right? So S is going to be 1. So let me now erase the signal part of it, okay, because we are going to make it as 1. So this values are going to be changing, this XOR input, and because of the XOR input is changing, these values out of B will be changing, and of course whatever intermediate results are will also be changing. Okay, A value will be same, but these values will be different. Now let us look at the value. Now S is equal to 1. I want to do a minus operation, so I give B as 3, okay, and then perform minus 3. Now when I am giving S is equal to 1, this is what is happening. This is 1, S is equal to 1, this also 1, and this is 1, and this is 1. Now what will happen? 1 on 1 will be 0, and this is 1 on 1 will be 0. This is, maybe I'll change the color here for the consistency sake. B value has become 0, this has become 0, this 1 and 0 is 1, and 1 and 0 is XOR is 1. Now what is happening? Whatever was the input 0 1 1 has become 1 1 0 0. Now this has become 1 1 0 0, which is nothing but 1's complement. Complement has been performed by the XOR. Now XOR is behaving like a NOT gate, because of we are saying that I want to perform a subtract operation. So we are using the same full adder but performing a subtract operation. So whatever we were doing manually, 2's complement is being done by the hardware. That's why I have to show it as a plus 3 and then perform the 2's complement operation. Now we did just 1's complement. Now what about the plus 1 which we are supposed to do? That is what is happening, because you are putting a 1 here, that signal is coming here as a 1. Now this 1 gets added to the input here, okay, so it's actually equivalent to adding 1 in our 2's complement case. So this is going to result in addition of 1, result is 1, carry will be 0 because we are adding 1 and 0 0. Now this is again going to be sum is 1 and the carry is going to be 0, and we have 0 1 1, so that is going to be 0 here and carry will be 1. And what is the input here? We said that it is 1 here, so this will be 1 0 1, so this is 0 and this is 1. Now what about the carries? Okay, This carry we are not going to be looking at it because it's signed arithmetic. We are going to look at both the carries together and then find out whether the result has been correct or not. So if we are giving to XOR gate these two carries, this will be a overflow flag which is not set because these two are zeros. Okay, these two carries are zero. So this is last two carries, and the result what you have got is 0 1 1. Okay, 0 1 1, 0 0 1 1, which is, if it is minus 6 plus 6 minus 3, it is going to be plus 3, which is correct. Okay, so we are going to treat it as 0 0 1 1 because it has given you a correct answer. Okay, so I don't expect you to explain this much in the given time. So if I drawn the circuit and then one of the inputs if I given, it will be okay. Okay, one arithmetic also is fine. So that is almost, we are coming to the end of the discussion. So before we close, let us just quickly see the diode characteristics. Question 20 is a very simple one. We are saying ID is the current here and VD is the voltage across the diode. Now, you know that this is the graph. A Q point is something which is operating currently. Now, how do we know? Suppose I have a resistor, and because we are normally connect a resistor, even a LED, we connect it. Now, some voltage is given. I call it as a VDD, and then current flowing through this is ID. Now, some resistor R is given. Now, what is the point? Now, suppose I have not explained the load point in our in my classes, but for the completeness sake, because B section has been told about this, so let me talk about that in case which makes sense. Just to understand what is happening as a load line. So, load line is nothing but the circuit which is feeding the diode. Okay, bias circuit, biasing the diode. Okay, now imagine the diode is not having any current flowing through that at all. In that case, what will happen? Okay, there is no current flowing. Okay, current is zero. Then whatever we see here, voltage will be VDD by, this will be, let me explain that first. Okay, important mistake is this. It should be VDD, VD, and this should be current. Okay, sorry about it, because this is the voltage we get. So we have to call it as VD and ID. So this is VDD by R, which is what the, if the voltage is completely zero, it's a short circuit, then it will be completely current will be conducting over this. So VDD by R will be the current, and this will be when we have no current flowing. That means it will be, voltage will be VDD. So this point will be VDD. So this is called load line. It's just for completeness sake I'm explaining. Even if you don't understand it now, it's okay. This is basically what we are to do is, a Q point is nothing but the current which is flowing through the diode, and the B in voltage, whatever is the voltage across this, because the rest of the voltage will be here. Okay, so what I expect you to do is only to explain the Q point is nothing but the current flowing through the diode and the voltage across the diode. That's enough. Even if you don't explain the load line is fine, but as long as this voltage, the X line is shown as a VD voltage and the Y is to be ID. Okay, because you know that V in voltage is coming here. Okay, so this comes to an end of this section, and any doubts maybe we can clarify it in the class. You can ask me later. Okay, bye bye.